Section 517.13 of the National Electrical Code, or NEC, presents a potential oversight regarding the installation of branch circuits serving patient care areas within magnetic resonance imaging, or MRI, facilities. Specifically, the section mandates a ground path for fault current by installation in a metal raceway system, metal-clad cable, non-metallic raceway with metal fittings, or other approved means. However, it doesn't explicitly address the use of non-ferrous materials, which are essential in MRI environments due to the strong magnetic fields generated by the equipment. These magnetic fields can interact with ferrous, meaning iron-containing, materials, leading to interference and potentially compromising patient safety and the accuracy of the imaging process. As a result, materials like polyvinyl chloride, or PVC, and aluminum are commonly employed for raceway systems in MRI suites because they do not exhibit these magnetic properties. This discrepancy between the code's general requirement for metal raceways and the practical necessity of using non-ferrous materials in MRI settings can lead to confusion and inconsistent interpretations by authorities having jurisdiction, or ODGs. Some AHA may permit the use of PVC, recognizing its non-ferrous nature and suitability for MRI environments, while others may strictly adhere to the metal raceway requirement, potentially necessitating the use of aluminum conduit. To navigate this ambiguity and ensure code compliance, several steps can be taken. Firstly, consult with the AHA to determine their specific interpretation of Section 517.13 in relation to MRI installations. This proactive communication can clarify expectations and prevent potential conflicts during the inspection process. Secondly, if the AHA mandates the use of metal raceways, specifying aluminum conduit as the acceptable material can satisfy both the code requirement and the need for non-ferrous construction. Aluminum is a non-ferrous metal that provides a reliable ground path while remaining compatible with the MRI environment. Thirdly, consider obtaining a field evaluation or a letter of interpretation from the National Fire Protection Association, or NFPA, the organization responsible for developing the NEC. These resources can provide further clarification and guidance on the code's intent and application in specific situations. The issue stems from the fact that Section 517.13, while emphasizing the importance of a ground path for fault current in patient care areas, doesn't fully account for the unique requirements of MRI facilities. The primary goal of the ground path is to provide a low impedance route for fault current to return to the source, facilitating the rapid operation of overcurrent protective devices like circuit breakers or fuses. This rapid operation is crucial for minimizing the duration of a fault and reducing the risk of electrical shock or fire. In conventional electrical installations, metal raceways inherently provide this ground path due to their continuous metallic construction. However, in MRI suites, the presence of ferrous materials can disrupt the magnetic field, necessitating the use of non-ferrous alternatives. PVC, while being an excellent insulator and resistant to corrosion, does not inherently provide a ground path. Therefore, if PVC is used, additional measures must be taken to ensure a reliable ground path is established. Aluminum, on the other hand, is a conductive metal that can serve as a ground path while remaining compatible with the MRI environment. The NEC recognizes the importance of grounding in patient care areas due to the increased vulnerability of patients connected to medical equipment. Electrical leakage currents, even at very low levels, can pose a significant risk to these patients. Therefore, Section 517.13 aims to minimize these risks by requiring a robust grounding system. The code also permits the use of other approved means for providing a ground path, allowing for flexibility in design and installation. However, any alternative method must be carefully evaluated to ensure it provides an equivalent level of safety and performance as a metal raceway system. When using non-metallic raceways with metal fittings, as permitted by Section 517.13, it's crucial to ensure that the fittings are properly bonded together and connected to the grounding system. This bonding ensures a continuous ground path throughout the raceway system. The size of the grounding conductor must also be appropriately sized based on the overcurrent protection device. This sizing ensures that the grounding conductor can safely carry the fault current without overheating or melting. Furthermore, the grounding conductor must be installed in accordance with NEC requirements to minimize impedance and ensure effective fault clearing. In summary, while Section 517.13 of the NEC may appear to have an oversight regarding the use of non-ferrous materials in MRI patient care areas, this issue can be addressed through careful interpretation, consultation with AHJ, and the implementation of appropriate mitigation measures. The key is to ensure that a reliable ground path is provided, regardless of the materials used, to protect patients and equipment from electrical hazards. Let's delve further into the technical aspects of grounding and bonding in MRI environments, considering the unique challenges posed by the strong magnetic fields and the sensitive electronic equipment used. The grounding system in an MRI suite serves several critical functions. Firstly, it provides a low impedance path for fault currents, as previously discussed, ensuring the rapid operation of overcurrent protective devices. Secondly, it minimizes electrical noise and interference, which can degrade the quality of the MRI images. Thirdly, it provides a stable reference potential for electronic equipment, preventing voltage fluctuations and ensuring accurate operation. To achieve these objectives, the grounding system must be carefully designed and installed, taking into account the specific characteristics of the MRI equipment and the surrounding environment. The grounding conductor should be sized in accordance with NEC Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. For example, if a 20 amp circuit breaker protects the circuit, the minimum size of the grounding conductor is 12 American wire gauge or AUG copper. If a 30 amp circuit breaker is used, the minimum size is 10 AWG copper. The grounding conductor should be run with the circuit conductors in the same raceway or cable, minimizing impedance and ensuring effective fault clearing. The grounding conductor should be connected to a grounding electrode system that meets the requirements of NEC Section 250.50. This section specifies the types of grounding electrodes that are permitted, such as a metal underground water pipe, a metal frame of the building, or a ground ring. The grounding electrode system should have a low impedance to earth, typically 25 ohms or less, to ensure effective dissipation of fault currents. In addition to the equipment grounding system, a supplemental grounding system may be required in MRI suites to further minimize electrical noise and interference. This supplemental grounding system typically consists of a network of interconnected grounding conductors that are connected to a dedicated grounding electrode. The supplemental grounding system should be isolated from the equipment grounding system to prevent ground loops, which can create unwanted circulating currents. The bonding of metallic components in the MRI suite is also crucial for minimizing electrical noise and interference. All metallic components, such as raceways, enclosures, and equipment frames, should be bonded together using bonding jumpers. The bonding jumpers should be sized in accordance with NEC Table 250.102, based on the size of the largest ungrounded conductor in the circuit. For example, if the largest ungrounded conductor is 4 AWG copper, the minimum size of the bonding jumper is 4 AWG copper. The bonding jumper should be securely connected to the metallic components using listed connectors or fittings. The use of non-ferrous materials in MRI suites presents unique challenges for bonding. Since non-ferrous materials are not as conductive as ferrous materials, the bonding connections must be carefully made to ensure a low impedance path for current flow. Aluminum bonding jumpers should be used with aluminum raceways and enclosures to avoid dissimilar metal corrosion. The surfaces of the aluminum components should be cleaned and treated with an antioxidant compound before making the bonding connections. PVC raceways do not inherently provide a bonding path, so separate bonding conductors must be installed to connect the metallic components. The bonding conductors should be sized and installed in accordance with NEC requirements. In addition to the grounding and bonding requirements, the NEC also has specific requirements for the wiring methods used in patient care areas. Section 517.13 requires that branch circuits serving patient care areas be installed in a metal raceway system, metal clad cable, non-metallic raceway with metal fittings, or other approved means. This requirement is intended to provide a reliable ground path for fault currents and to minimize electrical noise and interference. The use of flexible metal conduit, or FMC, is permitted in patient care areas, but it must be installed with a separate grounding conductor. The grounding conductor should be sized in accordance with NEC Table 250.122 and should be run inside the FMC. The FMC should be securely connected to the junction boxes and equipment enclosures using listed connectors or fittings. The NEC also has requirements for the overcurrent protection of circuits serving patient care areas. Section 517.17 requires that these circuits be protected by ground fault circuit interrupters, or GFCIs, or isolated power systems. GFCIs are designed to detect ground faults and to interrupt the circuit before a person can receive an electrical shock. Isolated power systems are designed to isolate the patient from the electrical system, reducing the risk of electrical shock. GFCIs are typically used in wet locations, such as bathrooms and kitchens, while isolated power systems are typically used in critical care areas, such as operating rooms and intensive care units. In conclusion, the grounding and bonding of electrical systems in MRI suites requires careful attention to detail to ensure patient safety and equipment performance. The NEC provides specific requirements for grounding, bonding, and wiring methods in patient care areas, but these requirements must be interpreted and applied in the context of the unique challenges posed by the MRI environment. Consultation with a qualified electrical engineer and the AHJ is essential to ensure compliance with all applicable codes and standards. Furthermore, regular inspections and testing of the grounding system are necessary to verify its effectiveness and to identify any potential problems. The testing should include measurements of ground impedance, bonding resistance, and leakage current. Any deficiencies should be promptly corrected to maintain a safe and reliable electrical system. The ongoing maintenance and monitoring of the grounding system are critical for ensuring the long-term safety and performance of the MRI facility.